So we filled in the dimensions of all the variables in the Darcy Weisbach equation. Now it's time to take the next step in trying to simplify the dimensions of each side of the equation and see if they're the same. Now again, there's some more text here I want to put into the report, but I don't want to bore you with me typing it all in. So I'm going to copy and paste from my notes. And again, notice that I am using extra new lines in here to make it easy to see where my sentences start and stop. But the other thing that I want to do here is go ahead and do some indentation that I don't have in my notes. So I'm going to indent this line to make it clear where this sentence starts and stops. And that sentence is just one line, so nothing's needed there. Then that sentence is one line. And this sentence is two lines, so I need some indentation there. So that's a paragraph of text, and it's saying multiplying or dividing by a dimensionless ratio has no effect on the dimensions, similar to the numerical effects of multiplying or dividing by 1. Therefore, the dimensionless ratios in the formulation above have no effect. Now, there's an important clarification here. Note this does not apply to adding or subtracting. Now, this is really important. You can't add a dimensionless ratio to another variable with dimensions. They just can't add. That's not something that can be simplified. So I want to make sure this is emphasized. Now, there are ways in Markdown to emphasize text. If I put single asterisks before and after this text, then this text would show up as italicized. But I want to make it bold font. If I put two asterisks before and after this text, now it's going to be in bold in the formatted document. And I could add a third asterisk if I wanted it to be both italicized and bold. But in this case, I just want it to be bold. So, and this whole sentence to be bold. So I'm going to put a double asterisk before and after this sentence to make sure that that whole sentence is bold. And I could do this anywhere. Like if I just want one term to be italicized, I could put an asterisk before and after this word dimensionless. It can go over or go around any amount of text in your narrative. And finally, dimensions for additions or subtractions can only be simplified if the dimensions of the added or subtracted terms are identical. So if you can add two variables that have the same dimensions, then it does simplify to just those dimensions. But you can't add two things with different dimensions and simplify the dimensions. Okay. So that's the text. The next step is to show how we're starting to simplify this math based on this logic. And as I mentioned here, the first thing that happens is that anytime you multiply or divide by a dimensionless number, then that number goes away. So let's take a look at our equation. And what we're saying is that multiplying or dividing by a dimensionless ratio doesn't matter, doesn't change anything. So this multiplication in this term, which is all multiplication, no addition or subtraction, and this dimensionless ratio also in that simply don't matter. They don't change the dimensions. And also dividing all of this by a dimensionless ratio also doesn't matter. So we can really start to simplify this just by getting rid of all of these dimensionless ratios. Now I've tried to set up this equation and make that fairly easy to do. This one doesn't matter, and that one doesn't matter. That gets rid of the 2 in our numerator. But this 1 in the denominator doesn't matter either, which means we're actually getting rid of our fraction entirely. So I can get rid of the fraction in the denominator and bring this indentation back in to show that all we have left is what's in the numerator. So let's see what that looks like and make sure it makes sense relative to our derivation. I can preview this. And we can see that if we get rid of all of these dimensionless ratios, then we're going to end up with just the acceleration and the hydraulic ratio, the hydraulic radius, and that 1/2 exponent showing our square root. Okay, so the next step is a little bit more simplification. And again, I have a little bit of text here. I'm not going to type in. I'm just going to copy and paste. What this is saying is multiplying the dimensions remaining on the right side of the equation yields the following. So I have a length per time squared times a length. That means the two lengths end up being a length squared in the numerator. I end up with length squared per time squared. So again, I can start with my original equation, and I can show that, well, this length can just be accommodated by making this a length squared. And let's see what that looks like in our preview. So algebraically, when we multiply a length per time squared times a length, we end up with a length squared per time squared. Next step, again, a bit more text here. So we're going to use the distributive property of exponents in that we can distribute an exponent among multiplied terms that the exponent is applied to. So from basic algebra, we can, I'm going to indent this line. There we go. We can apply that 1/2 power and distribute it to the factors within the base of the exponent. So that means, again, I'm taking my original math, and I'm just going to edit it to do the simplification. We are actually going to be getting rid of this 1/2 power. So I'm going to get rid of the left and the right in the exponent. And if we take the length squared and the time to the -2 to the 1/2 power, each of them to the 1/2 power, that means the exponent on length goes away, and the -2 becomes a -1. Again, we're taking these both to the 1/2 power, which means we multiply the exponents, and a 2 becomes a 1, and a -2 becomes a -1. So where does that leave us? That leaves us with the fact that the left side of the equation is a velocity, and it turns out the right side of the equation also simplifies to being a velocity. So what does this mean about dimensional consistency? So I've got some text to type in here. I'm going to copy and paste it from my notes. Let me just clean this up a little bit so I have some neat code. Let's indent this sentence. And again, put an extra new line at the beginning of this sentence. There we go. That's a little bit better. And let's go ahead and look at what this looks like in our preview. So we've shown that the dimensions of the left and the right side of the Darcy Weisbach equation are the same dimensionally. So it's a dimensionally consistent equation. Now what this means is that it's probably an equation that's derived from independent theory as opposed to just an arbitrary empirical relationship. A lot of the times the equations that we use that are dimensionally consistent come from a derivation from more specific theory about how the world works or how reality works. Sometimes, however, we just use equations that have a mathematical formulation or have a mathematical shape that matches the pattern that we're trying to look at in nature. And that is what we call an empirical relationship. It's the math is whatever the mathematical shape is might be good enough. And those are typically, those equations, when we apply those, are typically not dimensionally consistent. Now, this isn't perfect because sometimes things that are dimensionally consistent are actually purely empirical by accident and not necessarily from theory. So this is just kind of a hint about whether a given equation is based on independent theory or based on an arbitrary empirical relationship or not.